There he is. Is he big enough? Probably not. There he is. Final answer. 10 ln of... Didn't we even do this one? It'd be so easy anyway. ln of absolute value of x plus c. What's the next one? 18. 18. Final answer. But did you guys divide? It made it so much easier. X cubed over 3, or 1/3 x cubed, minus 5 halves x squared plus 19x minus 115 ln of absolute value. X plus 5 is c.
The x plus 5 is supposed to be an absolute value.
Yeah. The reason being is because there's no like squared. You know what I mean? So just keep it in the absolute value bars. If it's to an even power or an even powered root, we can take it out. Or if, say, the x was squared on the inside plus 5, that'll always be positive, so we could also take it out as we're done. You could put the 115 up, or you could leave the 115 down. Either way, number next one. 26. Thank you. Ew! Gross! Who did you guys make you? Wait, remember they don't show their U sub. Who did you make you? Here's the final answer. Yeah, I would make you x minus 1 as well. I totally agree. I would make you x minus 1 as well. But then you had to use integration on crack on top, right? And long story short, if you did U sub correctly, and you were like, ew, there are extra x's. Actually, you guys probably have a question on 26. Do you want to peek at him in detail in a second? Okay, let's come back to him. I'll do him on my iPad where I can write so much easier than with the mouse. There. Number next one. Okay, 32. Final answer. Negative 1/5 ln of cosine of 5 theta plus c. This would have been impossible without the new formula. Yeah, Bridget.
Oh, never mind. Yeah.
Negative 1/5 ln of cosine of 5 theta. Sorry, absolute value. Plus c. Number next one. Oh, that's way down. Ew. Why write a decimal? That's gross. 1 minus 2 ln 2, or 1 minus ln of 4. Don't worry about the decimal. That's gross. 1 minus 2 ln of 2, or 1 minus ln of 4. I'm saying that because the AP, I almost can promise you, would pop that 2 up and make it 2 squared. 1 minus 2 ln of 2, or 1 minus ln of 4. Next, even. Look at us busting.
I misread the homework. I thought you gave us a proof.
You're a little salty. A. Exactly. Make the U the bottom. A. Any more?
108.
Yeah. Make U the whole bottom. Does that make sense?
Yeah.
And then 108.
Yeah.
You had to go back to review stuff for 108. You had to do y minus y1 equals m times x minus x1. You can't find m without a derivative. And you can't find y1 without plugging and chugging. Letter B. You gotta find area using the integral. You gotta find area using, well, you set up the integral. Sorry, B is just writing the integral. Sweet. C is solving for the average value. Now, here's the crazy thing. They went ahead and wrote a decimal, which means if there's a decimal, guys, you shouldn't have shown any of this work. Because you could have just plugged and chugged it to your calculator. Otherwise, you should have left it in the nice, long, complicated version. So the one thing I want to show you guys, if you are, or if the multiple choice are decimals, that would be a calculator problem. And so you can just go ahead and use your calculator to go from here to there and be done. But if it is a long answer, you would have had to go all the way down to this messy thingamabob, stick it to the man, and you would box it. Actually, come here, stick it to the man, box it, and be done. Who cares? You have all your numbers in there, right? Anyway, so long story short. Quick AP tip. Any more evens going once? Going twice and gone. Oh, sorry, A and B. Yeah, right there. A tangent line, B is setting up an integral expression. All right, I'm going to go ahead and go to 26 because you guys had a question on it. Then we're going back to section 4.7. ¿Dónde está? Aquí. Do you guys have the problem for number 26 real fast? You can help me out.
The integral.
Okay, hold on. Thank you. Just making sure you had it. Okay, number 26. Let me go ahead and get a black marker already. And let me get a nice snazzy box to make it pretty. Number 26 is the integral from
Of x. No, of x.
Oh. of x times
Times x minus 2.
all over
X minus 1 cubed.
All right, cool kids. We were talking about just a second ago that I would make u equal to who? Yeah, I agree. Du is equal to, now can you guys notice if you're looking at this, does this guy seem to really help us out with all of this mess up top? No. Okay, so this looks like an integration on cracky one. What should you do? Solve for x. So we go back to the u and we say, okay, the same way that we can take this guy and solve for dx, which really doesn't make, why did that just turn into a 0? What? I don't understand. There must be some sort of pre-built something. What? I don't get it.
That's so weird.
I hit something and I don't know what. Oh, that's what I hit. Interesting. Hey, wait. Look.
All
What?
of x.
Nice. It just makes shapes out of whatever you draw. Anyway, sorry, I'm having way too much fun. Undo. That is kind of cool. But not for right now. Oh no. Okay, the same way we can solve for dx equals du, we can come back up top and we can say, hey, x is equal to u plus 1, right guys? Okay. So then coming on back, we would go ahead and plug in. We got u cubed on the bottom, we got a du over here, and we have u plus 1 times u plus 1 minus 2, because we're plugging in for x, right? Does that make sense? Then we have to simplify a bit, meaning we have u plus 1 times u minus 1. And as all good calculus students know, just kidding, experienced calculus students know, is there a division rule for integration? No. So we can't do anything until we do. We gotta break things up, right? And we can't break things up until we multiply the top, right? That's what I did. And then we gotta go ahead and, can we heart it? Yeah, that's legal. That's right side up. And we end up with u cubed over, no, u squared over u cubed is 1 over u. And then 1 over u cubed. You guys see it? Taking one at a time and simplifying. I'm going to rewrite it again. Don't worry, I'm not jumping too far. We end up with the integral of 1 over u minus u to the negative 3. Now question, why did I change this power, but not that one? Got it. And the special rule is we're going to go to ln for the first one and power rule for the second one. So we're going to end up with ln. The integral is gone. We're taking it. Minus u to the, up it by 1, negative 2, divide by negative 2, plus c. A negative times a negative is a positive. Then we can go ahead and say ln of, who is u? X minus 1. Plus 1 over 2. I'm going to take this little negative 2 power and say, hey, you can go below. So 2 times x minus 1. Quantity squared plus c. Good enough. Done, 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 done. How'd we do? It's not impossible. It was tricky. But remember, no product rule, no quotient rule, so we got to multiply and divide stuff as much as we can to simplify it. And then go back to our basic rules. Anybody still writing 26? Going once? Going twice? Go ahead and turn in your spirals to the beginning of 4.6. In just a second, I will call you back by groups. But for right now, and if you have your 4.5 homework done, you can show me. Huh?
If you have cosine t over 1 plus sine t
Over 1 plus 10. The bottom.
is it always going to be over 1?
Sometimes there's a square root down there that might go inside. Now, I'm not saying this is an everyday thing, but I did say something about, you better have 4-6 done tomorrow. You guys need to start listening because I need you guys practicing. Okay. While I call you back by groups, you guys are writing down some very important formulas in 4.7. You guys are writing down some very important formulas in 4.7. I should say very tricky. They are important. I should say very important. They are important. Oh, the one thing I forgot today. Somebody have an extra pencil. To make life easy, group number 1, point your spirals towards me so I can see page 351. Page 351. Oh, that's rough. Jason, does it say 351? I just can't see it. Good. Oh, yeah, can you show me that one? That's it. Group number 2, point it towards me. Nice. Brandon, got it?
Oh, wait a minute.
Oh, Aaron, don't got it? Remember, you can always show me later for partial. Got it. Group number 3, let me see. Oh, you were absent yesterday. Eileen, you're okay. Do you have 3.5 done?
Yes.
Sorry, 4.5. 4.5. Okay, you can show me during the day. Okay, is that okay? Cool. Group number 4, Corey and Ella. Aw, there we go. Corey, you can show me later. Charlie's group, let me see it. Okay, but that's 4.5? Good. And Alan's good. And then that's 4.6 or 4.5? Okay, but you got started on it? Okay. Keep going on it, Jeff. But I will give you the partial. And Charlie, I'll give you a little bit higher partial. How about that? Going backwards. Ryan's group. Got it? Ah, nice. You have 4.6? Okay. I'll give you a higher partial. Maya, do you have 4.6? Ryan's group, let me see. Got it. And Andrew's gone. Ethan's gone. Much fun with basketball. And you guys. And then Sarah, let me see. What do you got? And Haley, 4.6. Remind me, did you have it ready or is that coming?
No, I should.
Okay. I remembered 4.5. That's right, you went back.
Do you still have the working group pulled up behind that?
Yeah.
Really?
Oh, it's right there. Kiddos, what was the dilemma we saw yesterday when looking at things that will need these formulas? How similar to these look with other things that you've seen in homework recently that didn't need these formulas? Yesterday, remember? I gave you 2 examples and I said which ones are old-fashioned and which ones are new. Which one is old-fashioned? Which one is new? And you guys, it was really hard to choose at first, right? Most of you chose number 2 as old-fashioned, but it's not. It was new. The trick with these formulas, a few of you are still writing. Why don't you finish it on up? The trick with these formulas is they don't look like they're going to anything trigonometric, and yet they are. They don't look like they're going to anything trigonometric, and yet they are. A couple more seconds. Can you guys just take a second and go find for me, oh, I'm very fun too. Go find for me your inverse trig derivative rules. If you want to go to your table of contents and find it that way, or get out your forever cards and find it that way. More, yeah, derivatives of interest. So go find a section. 2-6. Forever 7 or 2-6?
17.
Oh, 17. Forever 17 or section 2.6? I was just checking. I forgot what the choices are. On the off chance. Okay. Da-da-da. Wait, what? Okay. Oh no, what just happened? Okay. Question. Don't these look like those rules kind of backwards? Kind of. What's different? There's no u prime, but that's okay because what do we have in these integrals that kind of represents u prime? Right? So we have to do the whole u priming thing when we do our u sub. So we have to do the whole u priming thing when we do our u sub. What else is different though? The a. The a. The a is different for a very particular reason, and we need to memorize the a for a very particular reason. So it'll be way easier to memorize these formulas with a's than to try to go back to 1 minus u squared minus 1, and u squared plus 1, or 1 plus u squared, however you found a arctangent. So, long story short, these are almost those derivative rules backwards. The a's are there for a very important reason we will see today as we do examples. Bridget, go ahead.
Christy, can you go back to the first 2 examples?
And as I go back to the first 2 examples, since you guys have those derivative rules there and ready, do you see at the very bottom of the last 2 examples what I put? Derive. Sine inverse of 3x. How would I use the rules that you guys are currently or did look at in order to derive sine inverse of 3x? Good. Derivative of the outside would be 1 over the square root of 1 minus u squared, right? And u is 3x squared times u prime, who is 3. So we're using the derivative formula for sine inverse. To remind ourselves of how this thingy works, 1 over the square root of 1 minus u squared times u prime is the old-fashioned sine inverse formula. Kiddos, what was different between this answer and this integrand? Nothing except the 3. So what did we end up with in order to compensate from our u sub? The 1/3. Because the 1/3 times the sine inverse of 3x derivative would work out to be, right, what we started with. But what is one of the trickiest things? So there is a 1/3 in this answer because we need a 1/3 in order to get back, to get back to what we had in our integrand. But what's the trickiest thing in these examples? Knowing the difference and choosing the u very differently than we have up to this point, right? On the left-hand side, we would choose the u to be the whole under square root thingy. On the right-hand side, we're going to choose it just to be the 3x. Ugh. So we have to get really, 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 really used to these derivative rules. Now, the page I keep on skipping, and you guys do not need to write down. The page I keep on skipping that you guys do not need to write down is just a quick little remember when we first figured out how to take the derivative of inverse trig. We had our little derivative of inverse functions formula. That's like a forever card, right? If you're given f of a equals b, then defined f inverse prime of b. No. F inverse of a equals b. There we go. To find f inverse prime of a, we have to do f prime of f inverse of b, something like that. I don't know why it's not coming to my brain right now. We changed it this year. It's not stuck. Then we figured out how to take the derivative of cosine inverse using a formula. And we said cosine inverse, that's actually like an adjacent over a hypotenuse thing. And so we were able to say, you're the adjacent, you're the hypotenuse. We can plug in a little Pythagorean thing to figure out the other side. And then we said the derivative of an inverse is 1 over the derivative of the function, which would be sine of f inverse of some sort of quantity that we're trying to find, like a or b. And then we had to go ahead and come back to our triangle, and then we figured it out, because then we said cosine inverse of who? U. There we go. We come to our formula, and we can say, what is sine of cosine inverse? Well, sine of this triangle, sine of theta, is equal to opposite over hypotenuse. And that's how we got our original formula. The same way we use triangles in order to solve with, then we need our u prime. With the derivative formulas, we can technically use triangles to solve for inverse trig as well. Inverse trig integrals. Let's go ahead and just do another example. So we have the example, 1 over 9 plus x squared. 1 over 9 plus x squared. Now I'm going to go ahead and actually use a derivative rule that you guys just looked at. I'm not going to use the forever card rule quite yet, but you are going to see how it's so much better to memorize the forever card rule than to go backwards from the derivative rule. You guys just looked at all your your inverse trig derivatives. My question to you is, does this seem to match up with sine cosine inverse, cosecant secant inverse, or tangent cotangent inverse? Tangent cotangent, and more specifically, since it's positive, tangent inverse, because there is no square root, right? There is no square root. So therefore, sorry, this is annoying me a little bit. Go away, thank you. Okay, as we look at this, we're going to go ahead and quickly review. Hang in there, guys. I know the air isn't turned on, but you guys are doing all right. It's Friday. If we think this is a tangent inverse of somebody, isn't the tangent inverse formula 1 over, and just for sake of argument, let me do this real fast. Let's do tangent inverse of x. Isn't that 1 over 1 plus x squared? Right? So question, does this perfectly match? No. Who doesn't belong? The 9. So if we were to memorize the forever card, and if we were just to know this rule really, really, really well and say, hey, let's go backwards, we would have to make this match, meaning we would have to pull out, you guys ready? It's a little crazy. We'd have to pull out a 9 to get 1 plus. Ooh, but how do we pull out a 9 from x squared? Yeah, we can. We divide. Check it by distributing. Does it mean the same thing? 9 plus x squared. When you factor, you divide. So dividing 9 by 9, you get 1. Dividing x squared by 9, well, that doesn't really simplify. Then you would have to say, aw, stink. This doesn't look quite right according to the formula anymore, right? That still doesn't look right. Well, it would look better if we said, maybe we have a u. And who would our u be? Or, haven't you guys learned 1/3 x is a lot easier to write? Especially if you're going to do du. Who's du of 1/3 x?
1/3 dx.
Follow your system. So who's dx equal?
30.
Multiply 3 to the other side. Now it's time to plug in. What can I do with 1/9? Yeah, I can pull it out. 1 over 1 plus u squared times 3du, right? The 3 can come out to join the 1/9 and I'll get 1/3. Now does this look like the formula up above? Finally. So now I can go ahead and say, oh, all right. This will be 1/3 tangent inverse of u plus c, which is 1/3 tangent inverse of x over 3 plus c. Now I solved this one entirely just thinking of the original tangent inverse rule and making the inside match the derivative. Making the inside match with u sub. But wasn't that kind of tricky? Like pulling out the 9. Who would think of doing that, right?
Mm-hmm.
So hence, I'm not just going to have us work backwards from derivatives of inverse. Instead, can I go ahead and show you an alternative way of solving that's easier? But you have to know the forever card. Let's take the exact same example. Let's write the integral of what we had, 1 over 9 plus x squared dx. And let's, instead of comparing it to the derivative of tangent inverse, let's instead compare it to what we now know is the integral of 1 over a squared plus u squared du. What does the forever card tell us? Of? Good. That's our integration rule. How can we use it? Exactly. Think of 9 as 3 squared, or think of a as 3, right? So who's a? 3. Who's u? Who's du? 1 dx. Oh, that's not bad, right? Because now I can plug in and I say I have 1 over a squared plus u squared du. Doesn't that just fit in perfectly? Well, I was just having us notice that now this lets us go straight because now it matches perfectly. This lets us go straight to the conclusion, which says, hey, yay, the answer is 1 over a, which is 1 over 3, arctan of u over a, x over 3, plus c. Dun, 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 dun. So we're going to memorize these forever cards, and we're going to learn that. It doesn't mean the forever card, like these types of problems are always easy, but we just saved ourselves all that crazy work of making it match the old-fashioned rule, because we're like, hey, it's probably going to be messier than 1 plus or 1 minus under a square root, or u squared minus 1 under a square root. Maybe there could be some numbers too, and we can deal with those, and we'll simplify our lives if we just memorize our forever cards. That's why they're called forevers. So let's go ahead and do some examples using these integration rules that you guys need to be studying. Just looking forward to the future to let you guys hopefully be further motivated to work on calculus this weekend. Our test is next Thursday, which means the forever quiz will probably be Tuesday or Wednesday. This is our final forever card. Ooh. No, not of the year. I mean of this chapter. Actually, we might have one more forever card on Monday. I apologize. We might have one more. But he's not long. He's short. So, be studying your forevers. Get your forevers up to date. And I said I would try to... Oh, we already did this example. That's silly. I need to get them updated this weekend. That's what I was saying I would do. That's my job. All right, cool kids. We already did that example, so let's not worry about him. Let's go ahead and start with examples 2 and 3. My question to you is, what integration rule does number 2 seem to match? Which one though? Arc sine. Square root of 1 minus somebody. Oh. Okay, hold on. So, we have to kind of look at this a little differently. It's the square root. 2 can come out, right? No big deal. Okay. Who's being squared?
2x.
Wait a minute, guys. Why wouldn't we just do our normal u sub and make u equal 1 minus 4x squared? Yeah, because if we go here negative 8x dx, guys, is there any x's to cancel out for us? No. So that's why we're saying we want to use these new rules. Who is u? Look at your rule. It's 2x. Look at your rule. We're learning how to use them. 1 over the square root of, wait, who's a? Oh, a is nice in this one. He's an easy one. Who's du? Good. We can still do our dx is equal to 1/2 du, right? We just have a little more to plug in now, but now we can say, we have our 2, we have our integral of 1 over the square root of a squared, whatever, 1 squared is 1, minus u squared times 1/2 du. What happens with my 2 and 1/2? And now I can jump straight back in my formula to the answer. If I have the integral of 1 over square root of a squared minus u squared, the answer is arc sine or sine inverse, same thing, of who? Of u over a, or 2x over 1, right? Plus c. Dun, 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 dun. See, we just gotta make it match our formula and then we're golden. So when we go down to the next one, can you guys identify which formula this one's talking about? I see secant also. How do we know? Look at the arcsecant formula. Do you see how it's u squared minus and not minus u squared? And in this one, I see the formula coming below. Yeah. I'm just going to pull out the 4/3 because he's just messing everybody up. Nice. I was going to actually show that, but some people are saying, why don't you just pull out the 4? And let's see why they're saying that. You'll get 1 over the square root of who is being squared. So we can go ahead and say 3x is my u. If my u is 3x, I think I want to keep that 3x on the outside, because then I can say something like u equals 3x. What does a equal? U squared minus a squared is 2. Du is equal to 3 dx. So dx is equal to 1/3 du. We end up with 4, and technically, once we go to plug in du, we will have a 1/3 that we can pull out. We'll have 1 over u square root of u squared minus a squared. How's that look according to our formula? Does it look all right? To go straight back to, we have our 4/3. Uh-oh, how's the arc sine formula work? 1 over a. Arc sine, I'm writing secant, sorry, arc secant. I'm writing secant inverse because I ran out of room. Secant inverse of u over a plus c. Bridget, I'm sorry, again, what's that?
Why did you pull out the formula from the same time?
We could have, but when we were looking at the formula and comparing, we saw that 3x was going to be the u from the 9x squared. And the formula says u times the square root of u squared. So we're like, wait, we want the 3x on the outside to match the formula. Now, kiddos, here's the long story short. I'm not going to spot check 4-7 on Monday. So some of you guys got a little behind this week, catch up this weekend, and you can be with everybody else on Monday. I'm not spot checking 4-7, but wait. 4-7, we are going to get started on a worksheet, which is supposed to be the last 2 days. The last 2 days of this chapter before we review and then our test. we'll take a day and a half on the worksheet, which means we'll work on 4-7 just a little bit more. For some reason, my notebook is being weird. I don't know why. We're going to work on 4-7 just a little bit more because we did not get to the more hidden, not so obvious examples, and I don't want you guys to think that you have to do all of homework when we haven't seen the complicated ones. So, start 4-7, catch up on the rest, get down your forever cards, and we will be ready to go for next week. Mindful kids, if you have questions, come during lunch. I think I have a meeting right after school. I'm sorry, that's another reason not to have homework due on Monday. We'll have it due Tuesday. Bye.